For one, actually, let's get started. It's my great pleasure to introduce the speaker of today's seminar, Mr. Curt Hamilton. Curt was one of us. He graduated from here, 2010, I think. Sure. Yeah, he was NC State University Park Scholar with a Bachelor of Science degree in Electrical Engineering and Economics. He's Assistant Design Engineering Manager for BWXT. And in this capacity, Curt is responsible for system design related to advanced nuclear applications. He has over 10 years of experience in the US and the Canadian industry, including system design, radioisotope system development, INC, NDE equipment design, deployment for manufacturing and in-service inspections. So today he's gonna give us an overview of their advanced reactor program. Yep. So please join us to welcome Mr. Curt Hamilton.
Thank you. Thanks so much for having me. I'm excited to be here. I don't think I've been in a building at NC State over 10 years. I've been back probably a couple times, but I'm excited to be back. So thank you. We've had a great day so far today, getting to meet a lot of students, professors, and I love to see hardware. Got to see the reactor. Had a good time. I appreciate the introduction. And so I'm going to go through some company overview. You know, as Josh and I have mentioned to some of you all before, we've maintained kind of a low profile traditionally as a company, so we're excited to be here today. Share about our background, all the different stuff we do, both for nuclear power plant related and some of the other stuff we do. And we're going to specifically talk about the BANR reactor that is related to DOE's ARBP risk reduction program. So I'm going to go get started. Feel free to interrupt with questions. That's fine with me, or hold until the end either way. So about 6,700 employees, a couple $1 billion company. So we're like a top 50 defense contractor in the US by revenue, even though most people haven't heard of us. We make a lot of heavy components in Canada. We make like steam generators up there. We did a lot of the replacements for the US nuclear fleet when they upgraded to the new Inconel. We made a lot of those steam generators. Can do fuel manufacturing, and we do a lot of support for DOE laboratories as well. And we're the manufacturer of all the remaining highly enriched uranium fuel for university reactors and other AGU-based reactors in the US. So ATR at INL, Hyper at ORNL, MIT's reactor, MERS reactor, and this also has an HU field reactor still. So we're scattered all over North America. You see there's a nice little dot up there. That's one of our new locations out in the west. That's part of our medical isotopes business. That's Triumph, is one of the largest cyclotrons in the world. It's there, we're co-located with them. And we've got a couple different chunks. So we've got manufacturing sites largely concentrated in the East Coast, heavy manufacturing in Canada, and heavy manufacturing in the US for nuclear power plants. As I said, we have the medical business, which also has a location just outside Ottawa, Ontario, up there for the medical business. And then we've got a scattering of joint ventures. And so those are sites where we'll do management and operations for cleanup. And we'll talk about it a little more as we go through the slides. But generally, we'll partner with our competimates or frenemies from contract to contract every time, kind of change it up, have new partners, and say we offer the best value this time. Use us, government. So way back when, there's Mr. Babcock and Mr. Wilcox up in the top left. They really came up with the water tube boiler. There's a really cool letter from Thomas Edison saying it's the best steam boiler that God has yet allowed man to make. And that was the heritage of the business. And so as that continued, we made a lot of different steam boilers. And that meant a lot of steam boilers for the US Navy. And that turned into, hey, steam nuclear. And that turned into, in the 1950s, the nuclear Navy. And the USS Nautilus, the world's first nuclear powered submarine. And then as that continued, about 5 years ago, we were a combined company that was coal power and nuclear together. The company split about 5 years ago, and the coal side went off and the nuclear side went off. And at that point, we got a new executive team that decided they wanted to take the money that we were making with our nuclear business, instead of frankly subsidizing the coal guys that weren't doing so well. Now we can take that money and do something different. And that something different is investing in acquisitions and R&D. So Josh and I, who are here today, we're from Advanced Technologies. which is not just R&D, but really more of a product development organization. So applied to things we can turn into products for the company, not just a pure research house, although we do a significant amount of work. It's also work for commercial customers, government. And then, yep, I'm already there. So we have a long heritage of being involved in a wide variety of nuclear reactor designs and different aspects of it. So we used to have a critical experiment facility in Lynchburg. We did the USS Nautilus. We had a research reactor in Lynchburg. And you can see it's been all the way through. So we were involved in the Jupiter Icy Moons Orbiter, which you'll see down here in recent years. Up top's the USS Nautilus. There's the USS Savannah, which was a demonstration surface ship. And now in recent years, we did some support for TerraPower. We had the Empower small modular reactor design that was rolled up, but we're still actively working nuclear thermal propulsion. We have BANR, we have a DoD microreactor program, and several other things going. As I mentioned before, we've got nuclear operations, nuclear power, nuclear services. So this is kind of the investor view of the business, which is three main chunks. So nuclear operations, that is the nuclear cores for submarines and aircraft carriers. After the Cold War, the government really down selected to one manufacturer, the best one, us, right? There's other parts of the nuclear reactor supply chain for the government. There might be a couple of competitors left, but we have the corner on several important parts of that market. That's about 80% of our revenue as a company. Nuclear power is also known as nuclear in Canada. So we have a huge footprint in the Canadian commercial nuclear power market. They have a really different power market up there than we do in the United States. And they're making huge government investments in rebuilding their CANDU nuclear power plants. A lot of investment. We're selling a lot of heavy components into those plants right now. And we also make a lot of the fuel. There's another vendor for CANDU fuel, but we make a whole lot. And that's also where our medical isotope business supports up through. I've spent a lot of time last few years. That was our first key thing we did in product development and advanced technologies, was doing the R&D and now full commercialization of a new way of making molybdenum-99 generators. It's a diagnostic medical radioisotope that outputs a relatively low energy gamma that you can view with gamma cameras. Right? And that's entering final commercialization. If you listen to our investor call the other day, we're just about to submit to the FDA. Very soon. And the nuclear services is what I talked to about earlier, which is both the half, that's the part that Josh and I are in advanced technologies, and the other half is the management and operations part. So that's cleanup of old sites that still have legacy, largely from weapons production, that still need to be cleaned up, like the Hanford site at Savannah River, places like that. And then it's also management and operations. So like Y12 and Pantex are places we used to have some of that work. We have some of it other places like INL. BEA is the group that runs INL. So INL is a government-owned laboratory, but it's operated by contractor. And we're part of the management team there at INL. And so that's why you saw it sprinkled all over with joint ventures. So nuclear propulsion, precision manufacturing is really the home for nuclear operations, right? So high precision build and run. Generally, that's other people say, we've got this design and this is exactly what you want you to build. We did have a foray into missile tubes, which was a non-nuclear part of it. And they did that in Indiana. The site in Tennessee is really where they do a lot of fuel material work. That's where we have one of our two category 1 sites that process HEU. The other one being in Lynchburg. And then in Ohio, we manufacture control rod drive mechanisms and other heavy components up there. Also at our Cat 1 facility in Virginia, that is the manufacturing location for the other research and test reactor fuel that we do there, that's HEU. And so as I was saying, we have the only 2 US NRC Cat 1 licenses. We chatted a little bit earlier. Josh is an expert on the Cat 1, 2, 3 license stuff. If you have any questions for him. There's not really any Cat 2 HALEU fuel facilities in the United States right now. And depending on who you talk to, opinions vary on how hard that would actually be to spin up if the demand was there. Kind of a chicken and an egg thing. Ask Josh if you want to know more about that. So this is the site's a little more detail, sizes, employees, and all the different capabilities. So I used to work right behind that, there's a little research park back there that I used to work in. And then these are the other large facilities that we have. Apparently that crane right there is one of the biggest ones in the Ohio River for loading stuff onto ocean-going barges on the Ohio River. So over to Canada, I was talking to you guys about this. Near and dear to my heart was working on this project, the Molly 99 project. You guys interested in medical isotopes? So I want a quick explanation of Molly. Yes, no. Silence, yes. Got a yes, that'd be great. Thank you. All right. So the traditional way you make a Molly 99 pig, you end up with a shielded pig, and in a radiopharmacy, we'll think about it backwards from that first. In a radiopharmacy, there's a thing that sits on the counter, and it has Molly 99 in it, which is decayed to technetium 99 metastable. And you want to run a little bit of saline through there, and then that results in a slug of sodium pertechnetate. And then the radiopharmacist counts that, sees exactly how much they got that day. And then they'll cut the doses and mix it with the right targeting agents called cold kits. And so like if you have a suspected pulmonary embolism, they'll mix it with a certain thing, squirt it in you, image you with the gamma camera, see what's going on. The challenge is how you get that Molly 99 to the radiopharmacy. And the traditional way of doing it, Brookhaven figured it out in the 50s, is that for a chemical reason I don't understand, if you take Molly 99 solution that was formed, where Molly 99 is a primary fission product from U-235 fission, take that, it adsorbs great onto aluminum. I don't know why, works great. You take a little bit of that, squirt it on the alumina, put that in a lead pig, you're done. The problem is that creates a ton of likely fission HEU waste because you only run those targets for like a week or two. And then the chemical separation technology is also uranium chemical separation technology, which is useful for other stuff, right? And so particularly the United States government was really interested in getting the HEU out of that supply chain. And we think we've got a unique solution to that problem where we have a way of irradiating natural aluminum targets. So they go into CANDU reactors. We're going to stick them into the CANDUs at Darlington, which is a OPG site up in Canada and Ontario. And then those are going to go in for a little while, not real long, like a couple weeks, something like that. And then we're going to take those, and the secret sauce is how you turn that into the generators. We do all that at our facility, and out comes a generator that just goes right into the existing supply chain. There's other vendors with other solutions that lots of them involve either fancy equipment that's different than just a generator that goes in the supply chain, or still involve uranium somehow earlier. And so we think we've got a really robust solution there, where again, you take the targets, irradiate them, turn that into the generators, all within our own single facility and put them in the supply chain. And we don't have any fission waste, and the other waste we have is also just not that expensive to deal with, right, which is a really nice advantage. Any questions on this stuff? Okay, got some nods, that's good. Nuclear Services Group and Advanced Technologies. So here's a picture of NASA, the NTP program rocket. And so what we're really focused on in there is, this is the reactor subsystem part of it. So you get cryohydrogen from some tanks you don't see up here. And it spits out down here really, really hot, several thousand degrees Kelvin. And that's really all that happens. It's, you know, hard to do, but that's just whatever temperature you can heat it up to is how much ISP. And so we're heavily involved in this, particularly that part of it. The other parts, you know, the cryo fluid management, the engine up here, the nozzle, those parts other people are going to provide. NASA's taking an approach right now where they're generally acting as a systems integrator for all of it. See the Artemis program and SLS for history about how well NASA does at that. But we're really excited to be a part of that program. And that's been a good one for us at AT for years now. And we're in a design phase on it now. We also do a lot of additive manufacturing of advanced materials in-house as well, in addition to the other medical isotopes. So, yeah. So this is where Josh and I sit right now. That place is about 60,000 square feet. We have a 10,000 square foot lab across the street. We're gonna turn both of those in and get 130,000 square foot facility across town. We actually traded it back. We traded part of our services business to Hamilton, and they traded us the building. And so we're excited to move over there because it's going to give us a chance to enhance a lot of our capabilities. That 120 number you see up there is going up to a number like 170 here in the next year. We're a little above that now. So
We're at 140 right now, so.
140 now, headed for 170. And so we're about to push out some job postings. If you need a job soon, come talk to us. And we'll be around after. And technical services, hit that a couple times. Those are spread all across as joint ventures. If you like to move around and you want to live somewhere for like 3 years, somewhere else, 3 years, move somewhere else, 3 years, that's the career for you. So we have a Tricep fuel manufacturing facility. We are the only US manufacturer to make irradiation tested uranium oxycarbide Tricep. So we made all the fuel for the AGR 567 experiments. We were involved in making it for the earlier parts of it, but engineering scale for AGR 567. So those were uranium oxycarbide compacts, Tricep fuel, graphite matrix that were put in these sample holders and put into ATR. ATR has this fancy way where they mix helium and neon in a blanket around the test capsule. And there's water around it, which is cold. And you want to actually test at the right temperature. And based on the fission heating in those compact sample holders, they tune the mixture of helium and neon to tune the thermal conductivity of the water. And that way you get a nice sample temperature that you expect. Right? And so AGR 567 is in fire right now. They pulled that experiment out. And so we've got a lot of capability at that facility though. We have the ability to downblend at the facility, and we can really, in the same facility, our specialty fuels facility, we can kind of make whatever fuel we want at a glove box level laboratory kind of capacity, right? But we have an engineering level capacity for TRISO at the hundreds of kg per year level right now. And we have, this actually has completed our conceptual design activity for a new TRISO manufacturing facility. And that's at those kind of 4 MTU per year kind of levels. That's the chicken and egg problem we were talking about earlier. If somebody wants to sign up to buy some versus us just building it and waiting, right? So it'll work out the right time. A lot of attention from NEI on the Haven side of things. This is the rest of the facility you'll see. So it's a solution processing facility. And we also have a unique capability to do full scrap recovery and everything in-house right there. So we can do uranium oxide, uranium carbide, alloys, nitride, oxycarbide. We can coat with ceramic, so SICK, that's the coating that's in the TRISO particles, right, along with the pyrolytic carbon, which is graphitic, and we can also handle refractory metals as well. Right in Lynchburg. So that's kind of the overview of the company. We're going to switch over now and hit BANR, our advanced nuclear reactor. Questions on the company so far? Anybody have anything? Okay. Great, thank you. So BANR, just a quick look at what it is. So we're going to go through a bit of a structured view of what's going on with BANR. We're going to start off with this little overview, what it is. We're going to talk about the background, how we work with a potential customer to come up with the concept, how that turned into this ARBP demonstration program, and then about what that risk reduction is going to look like and how we're executing that now. So the basic idea is it's a high temperature gas reactor, and it's got a core on skids, and everything is skid mounted. So you could produce everything in a factory, put it on site. It's a high technology readiness level, manufacturing readiness level. Does anybody in here know what a TRL or an MRL is? One, okay. So technology readiness level has to do with, yeah, not a student, so I'll just answer. Technology readiness level is how mature a technology is, regardless of whether there's actually a factory, right? So MRL is, could you go buy one right now? Is there a factory? Is there production capability to do it? TRL is, has it been demonstrated? I would say kind of in the recent past, right? So TRL ranges from 1 to 9. Bizarrely, MRL is 1 to 10. Why? A TRL of 9 is like, we have a spacecraft that targets a particular orbit. It's been on orbit, it works great, we're maintaining it, right? And it goes down from there. One is we have an idea. Two is we tried it out, right? And it kind of goes up through that. There's a notional valley of death in there where you get to, we have to commercialize it and prove it out, right? Somewhere in the higher numbers in the 5-6 kind of range. And so you'll see a lot of DoD customers and DOE now picking up this TRL, MRL language. It's a common way to compare how far along something is. And the finance people then think how expensive it's going to be to get it to the next level. There's an associated concept called advanced degree of difficulty, which is, okay, great, you're at a 5. Well, is it $10 or $1 bajillion to get this, right? And how long is that going to take? So we originally on this one worked with a customer and we came in at twice what they could afford. And then we started thinking about how do we, in the framework of ARBP, reduce the risk, which means reduce costs, right? And so that's really what this program's about. So we consolidated our efforts into this BANR reactor design, and that's what we're going to keep talking about. So one of the key changes is instead of UCO, switch to UN. I think you guys, smart nuclear folks, understand there's more uranium in UN than there is UCO. If you make, Tricep kind of fuel out of it, right? Leveraging our computational engineering tools and optimized fuel system for the core design. Advanced sensors, because this thing needs to be semi-autonomous, not so many operators. And manufacturing throughput, quality control enhanced through data science, digital twin, right? So this goes over HTGR versus conventional water reactor technology. So I'm just going to page through some of these key considerations so we understand more from the, we saw just have a nice light water reactor here, see the simulators, that kind of thing. Capital investment. You see on the water reactors, there are so many safety systems and backup systems and systems and systems and systems, right? There are a whole lot fewer systems on advanced gas reactors just by design. Cheaper, less maintenance, less stuff to inspect, right? When you switch to TRISO, you're essentially trading your containment building for some containment on the individual fuel kernels. So it's structurally a different approach to safety, right? And then that enables a lot more passive safety systems as well, more inherent safety characteristics. Constructability, for this particular HTGR, because it's small, we build that in a factory, so a lot of the same stuff you're used to hearing about SMR type things. The advantage here compared to an LWR SMR even that you could build in a factory is now you don't need a big concrete containment structure because you have your Tricep, right? Thermal efficiency, higher working fluid temperatures. That's nice because that actually gives you some flexibility to look at other process heat applications, hydrogen, that kind of stuff, right? Deployment timeline, we're really good at building nuclear reactors and factories. We do it all the time, actually. And we think we would be really good at building this as well. It's easy to get these to remote locations, put them on a truck, minimal construction, equipment, and personnel. There's some conversation right now about how do you build nuclear plants cheaper, right? And when you look at heritage builds, a lot of the heritage builds, they improve them every time. And they rotated in new managers to make sure they had the best ideas. And what that meant was different people were building different things every time. And as you generally think about when you mature a technology, it gets cheaper to build it. And most countries, nuclear, the next of a kind got more expensive and they built them slower, right? And so by bounding that, we think that you'd be able to get the cost down, right? It's modular. We'll talk more about it. Skid-based. And so you can swap things in there now, including whole bores. So instead of just a refueling operation on site, you would actually just pull the old one out, put a new one in, right? And you wouldn't need experts on site with all the qualified equipment to get in there and put your fuel in and not screw up, right? Remote operation, pretty self-explanatory. And then the flexibility, right? Electricity, steam, cogeneration. So we did in 2020 an industrial customer study, feasibility analysis, where we looked at 1,200 megawatts thermal, 100 megawatt electric from offsite source. And they were worried about a future carbon tax that would really change their carbon intensive way of doing this business right now. And that they really wanted to be able to do all of the process heat electricity cogeneration. You know, there's certain industries where when you want to do these higher temperature applications, putting a bunch of solar or wind and then trying to get electric heaters to get you the process that you need, it's just not going to work, right? And so folks, even in carbon intensive industries, are looking at decarbonizing the production of their carboniferous products. So from that study, we came up with this concept: 50 megawatt thermal, 5-year core life, thermal spectrum reactor. That base approach was still UCO TRISO, graphite matrix, graphite cladding, 1975, graphite moderator block, right? So kind of a standard HTGR approach at this 50 megawatt thermal size. Helium, a couple different power cogeneration approaches, and then mechanical controls, capability for passive heat removal. You know, the whole moderator and graphite matrix concept of having a large heat capacity with TRISO fuel, that's kind of part of the TRISO thing, is you have this big amount of thermal mass and you have generally lower power densities as part of the inherent safety associated with that versus really high power density PWR designs. Yep.
To clarify, the 5-year lifetime would be 5 years, forget about it, and after 5 years, pull out, put a new one in, just
Yes.
refueling between.
Yes. Is that right, Josh?
Yeah, the thought process is you gotta have a lot of infrastructure to do a refuel on the core, so why not put that on a more centralized location? Because a lot of these are in remote areas. Don't put that expertise there, just change out the core, take it back, refurb it somewhere else.
So is like that refueling something that BWXT would handle, or?
Possibly, we've looked at the economics of that, whether we would spin off some other business to say do that at a centralized location or work with another partner. Clearly, we provide the expertise on how to load it because we load the fresh ones. So, but the idea is you pull the rest of the core, refurb the vessel, go back and put something else in. So.
And as you said, refurb the vessels, so you'd reuse the vessels as well. It's just that it's not like you trash the entire thing, right? You take it somewhere, refuel that set of hardware.
Yep. Secondary question, with refurbishing the vessel, is there a limit that's been found so far to how many times can you refurbish, or so you say?
Well, if you think about it today, you on a big LWR, they have specimen capsules and they're all the time pulling and looking at them, trying to determine vessel weld fluids and fluids lifetime on the vessel and degradation. If you're taking this off site and I remove the core out of it, I have a lot better access to go in there and take a look at it. So I would say today, I don't know. I probably can get 30, 40 years out of a vessel, but it might be that I can extend that much farther because I know much more about the vessel without having a lot of it's easier to get at. So.
Yeah, it's hard to do inspections now on site for reactor vessel components, especially when it's buried in the middle of these plants, right? Hard to get to things like, there's been a historical on some of the PWRs, the dissimilar metal welds where you join the piping to the bottom of the reactor pressure vessels, right? It's a tough problem to get in there and inspect and prove that it's still good, right? And this would enable a different approach to those kinds of inspections. And this is that's a beam cell. So you see a TRISO graphite matrix, and then you would have the coolant would flow in this area here, right? Between which helps keep your moderator cool by running coolant between the TRISO and the cool. So this is our assessment of the TRL MRLs. I'm not going to go through every single one of them here. Sometimes you will notice areas like the reactivity control system and passive cooling where the MRL is actually higher than the TRL for the particular thing. Not weird, it's saying, yeah, the technologies that we expect to use aren't fully proven in this application, but the manufacturing capabilities there for similar stuff, right? So not a surprise to see it that direction. You don't see it on here, but you also often see the other direction where the TRL is higher than the MRL if nobody's really commercialized that sort of product. This is really leveraging existing supply chain to maximize both the TRLs and MRLs. So both ourselves and our customer agreed during the study that this is a highly mature concept to continue with. Anybody have any particular questions about any of the technologies? Okay. So the approach for feasibility was to look at a lot of case studies. And that included looking at electricity only, steam only, and cogen. 27 total cases, a range of use conditions. So different steam pressures, different temperatures, cogen, all those different options, along with varying feed water temperatures as well, right? But as we said, looked at all those things, way too expensive. Technically feasible, concept meets it. And what you'll see on some of this is, we're going to talk about this more with the layout, where you'd have multiple reactors, where you could have 2 reactors and then common sets of secondary side type equipment, where you could switch between either one. Whether one of them is refueling or a maintenance outage or whatever, that you could combine the secondary side equipment, and it'd be independent from the core side. So here you see the cycle for one of them, where you've got the reactor vessel, you have your primary coolant system here, and then that's a recuperator and a compressor, and then you've got your electrical generation here as well. So we think about going through with this and modeling at that level is really useful for talking to customers about what they want to try to do, right? And when you go through the case studies, each one of those change for each case study, basically. So at that point, enter the ARBP program. So ARBP, you guys are involved in some of the other ARBP programs. So there are 3 tiers to the overall program. One is demonstration. And so that's the X Energy and TerraPower demonstration programs, which you guys are aware of. We are in the 2nd tier, which is risk reduction. There's a 3rd tier, which is more like technology development, 30 years out, way far off, right? We're in that 2nd tier risk reduction slot. There's a mature concept. We want to go de-risk particular areas that we wouldn't be willing to go invest our own money in. We're interested in doing it because the DOE is going to share the cost for us to go reduce the cost of those technologies. The goal of it is to significantly improve the economics. So it's not just let's go investigate with bank technology, but actually do risk reduction that results in lower costs, so nuclear is more feasible, right? And it gives us the time and platform to develop the technology while the market matures. And it gives us a nice thing to come talk about as well. So again, we've talked about a lot of these things. So the 5 modules here for the reactor designs, what we haven't hit yet: passive inherent safety, and it's rapid to do the installation and refueling. I'm not going to dwell on this anymore unless you have a particular question here.
I will say one of the things about it is most of the time you have weird design constraints. This one was, we wanted to fit on the back of a commercially shippable truck. And so you got a vessel diameter, that's such a core diameter, that then sets your thermal power level. So that was a little bit how we backed into that problem, going a little bit different than normally saying a use case says they need 150 megawatts. A lot of people just say, I'll build a reactor that's 150 megawatts. We said, we wanted to fit on the back of a truck.
Yeah, can you talk a little bit more about the inherent safety mechanisms? I mean, are they kind of branching off of what we've seen in the more advanced, the Gen 4 type reactors, or where is it going? I mean, how is it going?
Josh, you want that one?
So, yeah, most of it's the Gen 4 capability that you've seen in HTGRs. We're not really reinventing the wheel there. So, you know, he's already mentioned the high heat capacity. So the other thing is, because we kept it at a certain power level, we're still looking at air cooling. So we can handle, you know, upside transient conditions, even while cooling type events, and you know, you can still passively cool. You can let it sit there and cook, and it'll be fine. It would vent to the atmosphere inside the containment dome or whatever you got there. Not really a containment, but sort of.
Yeah, this is just an aside. An interesting feature of the TRISO type designs is that if you have a point failure in the core, let's say something happens and you lose a whole TRISO compact, it's a really different accident scenario than if you lose, even just poke a hole in an LWR fuel rod. If you poke a hole in an LWR fuel rod, you lose the entire fission gas that's in the rod, right? But if you have a point failure in these, it's only the fission product inventory for the failure location. Okay. So transportable, I learned that they fit in the truck. You'd have a central control building. INC in there, minimal number of operators. In the electrical power version, it was a Brayton cycle turbine generator is what was considered here. But again, process steam, hot water cogeneration, just depends on the application. And the core for us, core, is the 50 megawatt thermal H2 yard version. This is a look at one of the BOP skid approaches. So you can see some of the main components, including the feed water heater down here, your control electronics. You're gonna have processed water associated with it, reboiler, low pressure turbine, generator, all this. And again, you build it in a factory in a skid-based approach, and there's a lot of precedence in other industries for building out bubble skids, this kind of stuff. The skid-based design in the vault, what you saw earlier was that you do have this in the vault. These are on rails, so you bring them in there. And you do need, a helium cleanup system to process the helium. And you do have the, helium supply chain issues where you're gonna have to get the helium, get it there, and store some on site. But
I'll say this, at least one of the major customers we're talking to, helium wouldn't be a problem, so.
depends on the situation. Yep. Yeah, and so these would just be individual, I don't know, is confinement the right word for that? Or is it really for shielding?
It's really for shielding. It's kind of a burn quantum, we call it. So the idea is that it is for shielding. So the reactor itself is, you can load it in, load it out, and safety systems are there.
So this is what we saw earlier. You can have your VOP skids common to 2 reactors. So that could either be install one, install the other, or you can run both, right? Again, very flexible is the idea. We want to continue maturing the technology for the reactor while we can demonstrate that you can use in a lot of applications. Yep.
I have a question of,
Sure.
basically, depends on that here. I mean, how does, so you're basically serving 2 vaults with one system. How do you ensure availability if the skid system goes down for each of the vaults?
Yeah, it's part of the control system that we'd have to look at and try to control. I mean, it was a concept in this regard that we're putting out there in customer, that we've talked to a couple of end customers for this potentially. It's likely, we kind of said, well, we'll save money by splitting it. Realistically, I think it'll probably be one for each. Yeah. So, we were trying to make an economic case to a customer. Realistically, when you get down to it, he looks at it and he says, buying a separate BOP skid is not that much. I'll buy a separate BOP skid. So.
Yeah.
So if the boundary for the systems delivering safety functions is really limited to the vault, the balance of plant has nothing to do with anything regarding safety. So
Yeah.
you're not affecting.
So.
Yeah, and here you see there's a steam generator back here, right? So the primary systems and any fission products would all stay in here, right?
So in the BRA, we don't go outside.
So.
What's your separation between these vaults? Like how far are you piping this steam?
Not far. The site plan for a site of 6 of those sits on less than 15 acres. More likely 8 acres is what we kind of spaced out. But we put 15 for some extra ones depending on which country we might be. So extra space. Yeah, it's big, but at the same time, it's not that big when you compare it to the exclusion zones of the LWRs.
Sure, but like how much is that affecting your thermal losses? So piping the steam back far?
At least for the case we ran for the area, which was probably cold, it wasn't too bad. So if you consider some insulation on it and everything like that, you weren't seeing a huge amount of process losses that you need to take into account.
There's a question from the virtual host, probably earlier on, but it is. Do all SMR concepts involve highly enriched uranium?
So
Basically, none of them do. So I'll go on a quick discussion on that. A little history. The US handed out a whole lot of HEU fueled research reactors in the Atoms for Peace program. It was like us and the Russians saying, who wants one? Let's be friends, right? And then we continued to provide HEU fuel for those reactors over time. Sometime in the 70s, the United States government decided we didn't like the proliferation risk associated with that, and we began converting all of those HEU fueled reactors over to LEU. I think the US has succeeded in our mission to do that internationally with all the ones we supported, including the little tail on that dog is HEU medical isotope targets for Moly-99 production. There's still a tiny amount of exports, particularly to Europe, and maybe still to Australia. I can't remember. A little bit of HEU targets going out still while the Moly-99 supply chain gets fixed, right? There is no signal from the US government for even things like NTP reactors that HEU is an available choice. The 20% limit, which practically means 1975, everybody we talk to is only interested in that stuff. You know, from a purely engineering perspective, it sure would be great to have HEU, particularly for wake and train space systems, but I haven't seen anybody propose using it seriously for anything.
No, the statement that I make is the only way you're going to go to HEU systems is if there is a specific defense mission for the United States that requires it for a mass space constrained reactor. So, and there's a reason that certain ones continue to use that. And if there is that need, you would probably see it resurrected pretty quick into some defense program. So, which they might not even talk about it for 20 years until it happens, so, or after it happens. So, yeah.
But as far as commercial applications go, there's no, and part of that, even on the US government side, is the cost for meeting all the regulations when you go above 20% is enormous. The number of gates, guns, and guards and everything you have to have is like you would have a little tiny army following all of our space reactor stuff around if we had HEU space reactor core going anywhere. And so even in cases where it sounds nice, the cost of biting that off is enormous, even if there was kind of moderate justification, right? You're gonna have to really want to do it.
And let's just be clear, nobody in the United States is making more HEU. That ability stopped several decade and a half ago. So it's a strategic asset, so they're not likely to use it outside of that mission. And in fact, you know, we talked about Halo supply chain in some of our discussions today. Same thing there, you got a supply chain issue that you would have to overcome. Now, that's not to say on the world stage, HEU is not available. Russia and China both advertise that they have capabilities to supply that. But it's a domestic and policy item that, you know, it's interesting to look at. Policy or nuclear diplomacy in the world market.
Yeah. Do you have another question?
Yep, there are two more from the online post. What passive measures are foreseen in your design to prevent overheating of the fuel?
So what passive measures are seen to prevent overheating of the fuel? So a lot of it is what we're talking about, the heavy massive core. And you know, an interesting feature on these is when you think about a LOCA and a PWR, if you have a huge problem immediately, right? When you think about a LOCA and a gas-cooled reactor, it's not nearly as bad fundamentally because you're not exchanging a high thermal capacity liquid for gas, right? And then the ability of this size to passively air cool, where the ultimate heat sink is the nearby air. Right? And so the heat, because of the low power density, you're able to keep the fuel temperatures below failure. The AGR program generally came out with a 1250 Celsius operating limit, but a 1600 degrees Celsius safety limit for their fuel. And so you have several hundred degrees Celsius for your fuel to jump in a passive cooling scenario, while the heat begins to flow out through the vessel and through the mechanical structure and into the nearby air. There's other stuff you can do. You can put a tank of water on it, let it boil off. Think about, do you really, can you ride out your transient with your local water inventory? There's other stuff you could do too, right? To try to ride out the point that the air circulation cooling is going to continue to work. And that really just has to do with the exact system size.
The bigger they get, the harder you are to fly past technologies.
There's one other question. Do you have a remote application solution for allowing BANR not to have active personnel providing security while the reactor is operating?
Not to have to provide local security.
Most of the applications that we have been dealing with customers, we would probably, they already have security forces. We probably would just rely on them within that boundary to take over the duties of watching the nuclear fence line too. So in essence, it would be a shared resource.
All right, great. So we've kind of seen this one before. Here you get to see the bonus that there's your enrollment out there. And these are all set up for you to access them on one side, and you can be on the other side. If you had, you're going to have a huge shine path coming out of here if you just open that door up, and there's a spent core in there. And so you're going to need some kind of auxiliary shielding out that end to manage that, right? But you wouldn't expect there to be loose contamination when you open it up, right? So you're just going to have to manage all that. So as we get into the risk reduction scope, the way we thought about it, this is a product breakdown structure for the reactor, showing the different systems. So when you think about the control building, the process, the power conversion and process heat system, and the reactor system, those are the major systems. The technology in these doesn't really, we don't need to do anything with these to hit our cost reduction targets, which we're going to see in a minute. Here we have, when you think about the reactor skid, that is where we decided to focus on our risk reduction scope. So the fuel system, the reactor core, the reactor INC, the reactivity control system, and the passive cooling. Those are the areas where we think we can have an impact. So the rest of this stuff, we have the reactor concept available. We know what we need to do, but we made the choice in the ARBP program to only go after the purple boxes. So this shows how we plan to get the cost down and where we plan to squeeze that out of. So our industry study, here's the number, right? So you can see the different costs that form the cost of electricity generation. This is dollars per kilowatt hour. And by increasing the core power, extending core life, reducing operations and maintenance, and getting our better manufacturing throughput, we're going to be able to hit the ARBP application goals. And here's the reasons. So I'll just let you guys read those. I'm not going to read it to you. And by reducing the cost, that brings it into possibility for these areas, right? So, and other applications like defense applications, it's not just about the money, it's about the mission. Industrial people, it's really about the money. Yep.
Can you beat the next available power system, and can you beat it with a carbon tax on it? It's usually how it looks. So,
So specifically with regard to the fuel, UN. So that's the longest lead aspect of the program. We mentioned it earlier to some of you. We're doing core design sprints. We're actually using Agile Scrum and integrated facilitated team approach as you go back and forth between your mechanical like TH and your core electronics people to go through quick design cycles to come up with a particle architecture that makes sense for this reactor concept. And then we're quickly going to go manufacture that, and then we need to get it in the ATR to get the irradiations going. So when you think about the different blocks of risk reduction we're doing, that's the long lead one because it involves irradiation and post-irradiation examination, right? So that's what's been prioritized for us internally as we get going. Higher core outlet temperature, we got to take a look at, depending on the customers and the partners, that's where you got to trade on, can you do direct Brayton? Do you do combined cycle? Those kind of things. We're going to go over the SICK AM parts of it, which leverage some of the transformational challenge reactor work that was done at ORNL that we participated in. And then coupled with machine vision technologies while you're building it. Which is associated with, that starts getting you the digital twin, but also the AM data informed fire manufacturing compared to the huge amounts of in-process ND we do on a lot of legacy products. And then incorporating in-core sensors. One of the key parts of that is just a quick decision which ones we're really interested in, so we can get them into the test capsules, so we get the radiation data, right? So that is a little earlier in this scope as well, specifically for in-core sensors. Yep.
How are you going about deciding how many sensors to instrument with, what is magnitude?
I don't know the answer to that. And I know we're going through it in close conjunction with INL to decide what's going to go into the test capsules. I know INL previously considered some alternate thermocouple technologies, but I'm not sure if anything else is on the table right now for the core test. You know?
I don't know off the top of my head, but I will say there's nothing worse than having a capsule go into ATR and your sensors fail within a week, and then you got to ride it out and you don't really get any good data.
They had some degradation issues too during one of the first, I think it was AGR1, where part of the thermocouple cladding broke, and they had I forget what it was, a particular element got it out of thermocouple and started attacking the SICK. And so you got to be really careful with your test capsule geometries and understanding your prohibitive materials and ensuring that if you have any chemical incompatibilities, you manage that appropriately, as everything is going to heat up, cool down, and change dimensions on radius. Okay, so this is a tricep particle. To get everybody oriented, you have your fuel kernel. You put a porous carbon buffer around the fuel kernel. That gives the fuel kernel space to expand, and generally the UCO I think is going to expand over time with radiation. But the pyrolytic carbon graphite actually densifies radiation, and so over time they tell me that the uranium actually gets loose inside the ball. And then you put on a hard layer of pyrolytic carbon, followed by silicon carbide, followed by a protective layer of pyrolytic carbon. So you put all that together, and then you end up with the particles. And at that point, you overcoat the particles in a coating system with additional matrix. The matrix is actually a combination of natural flake graphite, synthetic graphite, H-tip, TA, and a phenolic binder. And so you batter all your particles, and then you dump those into a uniaxial hot die press system, where you smash them, and the hot die activates a little bit of the phenolic, and you end up with a little slug like that. But you need to graphitize that matrix now and convert the system into a hard ceramic compact, and you do that just by putting them in a furnace. So the furnace cycle is a single furnace cycle, but it goes through a separate pyrolysis and graphitization operation. And that results in fuel that can withstand extreme temperatures well beyond, and they act as their own containment. And so that concept was taken and turned into, well, let's swap out UCO for UN. That's going to get us increasing core power and extending core life. And then we can use advanced manufacturing techniques to print, largely these enable you to get the heat out, right? By printing these geometries. And this one, you print that, you pour the particles in there, you load it with SICK, and then you do chemical vapor infiltration to densify it. And the densification with CVI means that you have it in a furnace and you're putting in gas that converts to silicon carbide in place. And that results in a densified fuel. There's other ways of densifying stuff, right? That's the particular CDI process that would be employed here. And this does commercialize existing TOE development work. And so that's going to result in fundamentally higher fuel performance, which we think would drive down the cost by enabling the 5-year core life and the increased power. Question?
There's one from online. The van operators would obtain their license from the NRC, is that correct? The DOB is currently qualified their own operators. How would that change? How would this change that?
Well, that's going to depend a lot on exactly where it is. So if it's in the United States and it's a commercial operation, yes, it would be NRC licensed operators. Exactly how it would work, I think really depends on how autonomous the controls are and how that regulatory process works. But yeah, whatever civilian regulator it is in the relevant country would be the license grantor. Anything else, Jeff?
No, most new to reactors, I mean, if you look at the AP1000s, most of them are qualified on standard PWRs. And then they train on the simulator, and NRC approves that training plan to make them qualified operators to start up a new plant. You would expect some similar type of behavior here for an advanced reactor. So probably more involved because an AP1000 and an existing LWR look a lot alike. So.
NRC already has an exemption process for reducing the staff, the control of staff. Went through that process.
NuScale successfully went through the staff reduction process with the NRC.
Yes.
Okay.
X Energy is following the same process, and I expect all the other one of the same process.
Okay.
Going to zero control room operators, that's a different discussion.
Yes.
10 CFR part 53 may be able to handle it. But 10 CFR part 52, that.
We haven't considered fully autonomous yet, so but yeah.
It'll be a bit of a race between the autonomous space systems and things like this. The autonomous space system, you're not gonna, if you have radio delays because that system's close to Mars and there's no people on it, there isn't an operator, right? And so folks are gonna have to figure out how to solve those controls challenges. And I think that provides precedent for terrestrial operations potentially, right?
Kurt, I will give you a warning, we are close to time.
Yep. Well, this is the last slide. And so we actually have to finish signing the contract with DOE.
If you've never negotiated with the DOE, it's a long and painful process. So.
Yep. Got to get the credits done with ORNL and INL. And then we're going through a systems engineering process. So we'll go do our product requirements and then do all the requirements for each section of risk reduction we're going to go do. And just keep on with it and then get into manufacturing and testing. Oh, there was one extra, sorry, counted wrong. So it's a mature reactor design, but we've got to work to get there to the maturity. You got to work on the controls approach and the passive cooling. And then ultimately we got to find a customer that wants to take this across the finish line with us, right? So that's really it. I lied, but we're done. Anybody, if you've got follow-up questions, feel free to ask them. Just come right over here.
We have maybe 1 minute before 5. Maybe I'll ask for one question from the audience.
No, I answered.
Okay, so maybe one.
You guys answered.
Yeah, from one from the audience.
Sure. So you were talking about challenges for remote reactors, I mean, that are far away from, let's say, Earth.
Yeah.
And I saw that like your technology readiness level was around 7 for the reactor control systems. Is that, so I mean, essentially really just 2 points off, right, from being able to solve that problem?
7 means it's there. So it just hasn't been fully deployed, but the technology is pretty much ready for final deployment, right?
There's a different question there. 7 is for if I have operators.
Yep.
I have INC systems that can support a semi-autonomous control. If I was to go to an autonomous control, I'm probably backpedaling to more like a TRL 3-ish level. I'm just shooting from the hip there, but
Much lower.
yeah, we're probably still gonna have to go through what we know is the valley of death around 4 or 5 to get get up for an autonomous control. So.
Okay.
You talked about, if you develop one of these and then you start the cycle and all your, inline sensors then fail, how big of a problem that would be? Have you looked at using any non-intrusive or outside of the core reactors?
For the sensor technology, clearly we would envision some export detectors as well as import detectors, and highly, as always is the case, the prototype will probably be over instrumented compared to the nth kind. So.
I was wondering if you've done any kind of economic analysis based on like principal cost, but also the cost for 5 years for like removal and refueling and then put in place, like, because I would obviously elongate the amount of time it would take to like break even investment.
Yeah, so yes, as part of my job is to run economic models and look for minimum on multiple parameters sets. So, just 5-year refueling makes sense. How many vessels am I manufacturing from a heavy component standpoint versus could I refuel in situ, and what does the cost look like to have a refueling building on site? The aspect of a refueling building also means if I'm not quite plug and play, I probably have a longer outage too that I have to sustain as well. Versus if I can just pull one of those out of there and park a new one in, I'm only down for a week versus I need 6 weeks to take the head off and refuel it. So lots of different parameters, lots of different ideas to play with, and overall economics of the things. So.
On the back.
When I come online, the electrical cost estimate was around 2 times the current grid rates, is that correct? What is your target customer?
No, so the customer we had was, I can't say much about them. The customer we had, we were 2 times their rates, and I would say that they are in one of those remote industrial type settings. So we are definitely much more than 2 times the national grid that you would get inside of the United States. So I have a hard time thinking any micro reactor is going to compete in the national grid without a carbon tax of some substantial level to penalize. And then also, just the fact the U.S. national grid, the lower 48 has the space for solar, wind, and all of this. It's going to continue to build in renewables, and you can still use baseload nuclear in larger sizes. I think when you're talking SMRs and smaller to the micro levels, you really are looking at industrial remote applications, things that need high heat process and those types of things.
Okay, I think we have all the questions answered. Well, let's thank our speaker again.